This video is talking about the development of a secondary ion mass spectrometry depth profiling technique for the elemental characterization of multilayer thin films. What is SIMS? SIMS is an acronym for Secondary Ion Mass Spectrometry, is a technique in which the surface of an analyte is bombarded with a primary ion beam. This leads to an emission of secondary ions. The release of secondary ions after bombardment with high-energy ions is called sputtering. SIMS consists of several components such as the ion source and a mass spectrometer. The primary ion source with the highly charged ions are focused onto the sample surface and bombards it, thus inducing sputtering of the secondary ions originating from the sample. The ejected secondary ions are analyzed by the mass spectrometer to identify the elements present in the sample. It is important to note that the process takes place in a highly vacuum environment to ensure the ion beam has sufficient energy to ionize the secondary particles from the sample. There are two modes of SIMS, static and dynamic. Static SIMS is the ejection of secondary ions from topmost atomic layer, analyzing the surface of the sample up to 2 nanometer. Dynamic SIMS is the ejection of secondary ions from top few monolayers due to sputtering process, analyzing in depth up to several hundred nanometer. Dynamic SIMS can detect trace elements due to the in-depth analysis, while static SIMS only able to perform molecular characterization. Static SIMS uses low flux of primary ion bombardment, hence minimizing damage to the sample surface. Dynamic SIMS uses high flux of primary ion bombardment, creating a crater at the sample surfaces and damages it. Static SIMS is also called as TOF SIMS. It is a SIMS technique that focuses a pulsed beam of primary ions onto a sample surface, producing secondary ions in a sputtering process. There are strengths and limitations in using TOF SIMS. The strengths and limitations are shown in the table for comparison. Dynamic SIMS involve a main beam of high energy to produce depth profiling. The deeper the beam buries into the sample, the greater the ion flux consumes the surface sample. The factors that affect the depth resolution includes the crater edge rejection, ion beam mixing, and surface roughing. For examples, crater effect influence the depth profile shape by redeposition onto the analysis region by sputtering from the crater wall or sputtering directly from the crater wall. For example, in a case study of oxygen tracer diffusion in LINBO 3, SIMS is used for depth profiling. SIMS is able to detect stable isotopes as a function of position within a sample. Oxygen is being examined in this case study. However, there are isotopes of oxygen such as O17 and O18, which are minor isotopes of oxygen. The appearance of oxygen isotopes are caused by annealing of sample in a large volume of dry O218 gas, then the sample is quenched to room temperature. These are the results of the depth determination of the SIMS crater from the case study. Image A is the 3D image, Image B is the cross-section, while Image C is the depth histogram for TOF SIMS depth profile of lithium niobate. Niobium oxide and lithium oxide have a similar profiles to the O16 signal. These are the references used for the video. Thanks for watching.